So thanks a lot. Raphael, in his excellent talk, focused on PV forecasting. So I will focus mostly on wind power forecasting. And another thing which will differ a bit from Raphael's excellent presentation is that I will focus a bit on probabilistic forecasting and the advantages of using probabilistic forecast. Because it's obvious when you do a forecast and then you later see what is the actual wind power production, then you will most often make an error. And it's very, very important for assessment, for planning purposes and for trading purposes to be able to access this error in advance, because it's varying in time. Sometimes you can have a lot of wind power with basically no error, and another time you can have a lot of wind power, the same amount maybe, but with a lot of errors on it. So, and I've done this together with a lot of my colleagues and also a company who is running forecasting for wind, wave, and solar power and load, for instance. So I'll focus, as I said, on wind power forecast, and I'll touch upon some of the tricks as I see it in order to obtain good wind power forecasts. And basically all what I'm saying about wind power can be said about solar power, and if I'm not running out of time, I'll just show a few slides on the solar power forecasting. We have been involved in a lot of projects, and now the systems we have, and I'm old, so I have been involved in wind power load forecasting since 93, together with a lot of the companies who are involved with the power system in the northern part of Europe. One of the main projects or systems is the ANAMOS wind power prediction systems and the WPT system, and they are now, both of them are running worldwide, for instance in Australia, US and Canada and all over Europe and so on. In Denmark now, on average, 27 of the power load is coming from the wind. And that of course implies that very often we have more than 100% coming from wind. The political goal is that in about 20 years from now, we should have 100% coming from renewables. So we are going in that direction. Here is just an example on how you measure the point prediction, the performance, and of course the performance can be measured by the root mean square error, and of course it's best to have a low root mean square error. And this is just for showing one example. This is only a part of the model. This is only what is called the power curve model. And I'll come back to what a power curve model is in a moment, because a power curve model is a very, very important concept both for wind power and solar power forecasting. Now I will touch upon some of the tricks which are very, very important in order to obtain state-of-the-art performance in forecasting. And some of these tricks are to build adaptive and recursive and self-training models. So that means if you build up and add new wind farms, you will discover that automatically. But another reason for the system that it needs to be adaptive is that, for instance, dirtiness on the wind, on the blades of the turbine can cause the production to go down by, say, 20%. In Egypt, we have even seen 30% reduction in production. And if we then see after a heavy rainfall, it can be more or less clean and the production can go up again. So it's very, very important that the system is able to adapt to things like that. And also in Denmark, the trees drop their leaves in the autumn, and then the roughness in the terrain changes dramatically. And as Raphael said, the MET models basically have a very coarse or large grids. So we must do some local adaptation. So adaptivity is a very, very important thing you should bring home. That's maybe one of the most important things in the model. Another thing you should also know, now I'll talk more about uncertainty in forecasting. Having a first course on statistics, you have heard about Gaussianity or Gaussian densities. But wind power and solar power is far from being Gaussian. I'm trained in statistics, so and even I started by using assumed Gaussianity 20 years ago, but I learned the hard way that this is not good enough. So we need to do it's a wrong assumption, and I did that as well, but I will come back to why it's wrong and what we are doing instead. Here is a power curve model. This is for a wind farm, a large wind farm in the northern part of Denmark called Holmesbjerg. And it's a model which relates the production of the wind farm to the wind speed. So more wind speed give more production, and also to the wind direction. Because the actual surroundings, forest in the neighborhood, and the actual layout of the wind farm implies that there might be some shading effects even from the wind farm itself. And you might ask why I do have several power curves for this wind farm. The reason is that we are using MET forecasts as an input to this power curve model. And MET forecasts are wrong, they are biased. And when you look at a particular wind farm, they are maybe seriously biased. And they are biased in different ways for different horizons. So I can dig into these details, but that means that I need to calibrate or recalibrate or take into account the errors from the MET forecast. And the models we are building here is published in a lot of papers. At the end of my presentation, there is a list of, since I'm old, I have produced quite a number of papers together with my students and so on. And this is what is called an adaptive non-parametric model, which the results is, as you can see. So I'm not able to write down the functional relationship. It's not a functional or parametric model, it's a non-parametric model. And this power curve model is used as a static. This is, of course, a static relationship, for instance, between the wind direction and the wind speed forecast by the MET services, and then the expected wind power production. But this is taken as input to a dynamical model, which where I do have, which I can use for wind farms where I have online data. Denmark is actually also built up of a lot of islands. So we have different areas of Denmark, and in some areas they have online measurement from some wind farms, typically the larger one, and then they only have recordings from the accounting system for the rest. And by combining the data from where we have online measurements, in that case we can have a dynamic model, and combining this with the power curve model, we can upscale it to the total island or to the total region. So that's how we are setting up the forecast, so we can basically make forecasts for a single wind farm, a region, or an island, or the entire Denmark, just as an example. We're using exactly the same system for Australia, where we have set up the total forecasting system for both wind and solar power. Another aspect is spatio-temporal forecasting, because it's clear wind normally in Denmark comes from this direction. So by taking into account errors we see on the west coast, or even errors we see in the UK, which is over here somewhere, we can improve on the forecast. And by doing this spatio-temporal forecasting, we get improvements up to, say, 15 to 18%, 15 to 20%, I would say, based on what we know also. Another very, very important thing, and I'm giving a lot of practical hints here, I think, is that different MET providers have their different ideas of how the parameterization of the atmospheric model should look like. And by combining different MET suppliers, this is the Danish MET services, DMI, this is the Deutsche Wetterdienst, the German weather service, and we can also have a local wind farm MET service, for instance, built on the freely available US, the model from the US, GFS or something like that. And combining this MET forecast in our forecasting model gives a huge improvement, in fact. So that's a very good idea. Do not only use one single supplier. Combine the MET forecast from several suppliers. That improves the forecast. The way we now I'm talking a little bit about uncertainties. The way we are doing that is either by using MET ensemble or quantile regression or stochastic differential equations. I'll probably focus mostly on quantile regression and maybe skipping that one because I don't have that much time actually. Ensembles the Met forecasts are, methodologies typically generate ensembles, as also Raphael mentioned. And these ensembles are generated by perturbing the initial conditions of the weather system and then solving the dynamical equations or the differential equations. And then by counting all the quantiles, we can see what is, for instance, a 25% quantile. And here the three upper curves are the raw quantiles determined from the raw Met ensembles. But they are wrong, as you can see. Here's what we see actually later on. They are largely outside this confidence interval. So we need to do some correction, and we have built some models by which we can correct these Met ensembles so they span the correct probability space, so to say, or the correct probabilities. Quantile regression is, as I see it, for the moment, the most useful way of generating quantiles. This is one way of doing it, but it has some disadvantages which we can come back to, because it does not explain how the quantiles depend on explanatory variable, wind direction and things like that, temperature or whatever. But quantile regression is a model where an approach where you set up a model for one of the quantiles. For instance, a 20 or 25% quantile or a 90% quantile. And you can do that for all the quantiles. And you can explain the quantile as a function of explanatory variables, for instance, wind direction. So that's a very, very useful approach, and that can be done adaptively as well. So by doing that, we are able to, I'll not go into detail here, but what we can explain here is that the difference between the 25 and the 75% quantile is largest when we have forecasted wind power in the middle. And that's not surprising, since the power curve of a wind turbine looks like this. So it's when we are in this area we have biggest uncertainty. If we are here with a lot of wind, we don't have that much uncertainty. Another thing which was surprising for me in the beginning is that the uncertainty when the wind blows from the west is much higher than when we have easterly wind. That's for Denmark here. And the reason behind that is normally when we have wind from Russia, it's rather persistent. It blows for many, many days in a row, and it's almost the same. In winter it's cold, and summer it's warm, and so on. But when we have southwesterly wind, it changes every now and then because it's low pressure phenomena, which then change the weather from day to day, basically, or rather often. So the result of the forecast can look like this, where we have the different quantiles. So the most likely one are the deep blue colors, and the very most likely a point prediction could be the red one. And what you can see, of course, that the uncertainty can go down again. Here the uncertainty is higher than here. But one problem which is still missing is that when we then compare this, so this is a forecast which is generated here, and all these quantiles are calculated while we were here. And then the actual data is showing up as the dark curve here. And what you can see is that neighboring data points are correlated. So this correlation in forecast errors is very, very important thing to take into account as well. We do that by modeling the correlation in forecast error of different horizons, and this is simply the correlation coefficient between one horizon and another horizon. So that is modeling the interdependence structure of these forecast errors. The reason why this is important will be clear soon, because very often you have to decide on start and stop of units and things like that. And in order to do that in an economical or maybe also technical best way, you need to know how persistent these errors are over hours, whether they are uncorrelated or they are very correlated. That makes a lot of difference. So here is some examples generated by our statistical methods where we have used the correct correlation and quantiles for 7 days. Here we have, I guess, 5 different realizations which are having both the correct probabilities and also the right correlation. If you forget about the correlation but having the right quantiles, it looks like this. And of course this is wrong, as you can see. naked eyes. So, but people tend to forget about this autocorrelation in forecast errors. I will skip this. This is a more advanced method, which the use of stochastic differential equations is a method we are developing for the moment. It's not in production, you may say, or it's not really used in practice. But the good thing is that by that we can change the correlation structure as a function of explanatory variables. And leave it here for the moment. We have papers on it, and I'll be glad to talk about that also. At the end here, I will talk about what is the advantages of using the different type of forecast. The most simple one is, of course, the point forecast. Well, you only have one value for all future time points of the expected wind power, but as I hopefully convinced you, you should also have the quantiles, and this is one example of how you can illustrate the quantiles by these colors. And in some other, this of course doesn't describe the correlation, but by having the scenarios generated by the statistical tools, we can also describe the correlation in time, as you can see here. Pierre Pinson, who is in my research group at DTU, has showed in his thesis that using the uncertainties in the regulation market on the wind power that was actually the Dutch electricity market, then the value or the decrease of regulation was of the same size as compared to having a very, very advanced forecasting model compared to not having it. So it's a huge advantage of taking that into account in your business. This shows an example of a stochastic portfolio. 3 minutes? Okay. This is an example of using quantiles for optimization of a portfolio of production units. Here you simply somehow you have some limitations here. But if you neglect the uncertainty or stochasticity, you are doing like the green one. This is the expected value. But what you can do is, of course, you can have some back-off limits, so you take into account some uncertainty, but then you get something like this. And of course, the best thing is to take into account the uncertainty which you have at any point in time. So by doing that, you really get a much better optimum in your portfolio optimization. Another thing which is of relevance is when you're trading things on, for instance, on the North Pole, where we trade electricity power, then it can be shown that the bid, then we have a price for a bid, and then we have a penalty when the actual production deviates from the bid. We have a down regulation price and an up regulation price. And it can be shown that the bid which maximizes the expected revenue is actually this one, which is actually formed from these forecasted prices, or the mean value of these prices. And the most important thing, or surprising thing for me at least, was that for a very long period of time, the 75% or even the 80% quantile was the optimal bid. And of course the reason for that is that the penalties for up and down regulation is different. So you should be biased in your bidding if you should maximize your economical profit. Here is shown one example of neglecting the autocorrelation in forecast errors. If you should decide on balancing your wind by some other production or sizing some storage, if you don't take that into the autocorrelation into account, then based on 50 independent scenarios, you can see that your storage should be of this size. But if you do it correctly, the storage should be 5 times higher or something like that. Solar power forecasting is also, I will basically skip it, but the power curve model for solar power forecasting, which illustrates the expected solar power in clear skies, which we see sometimes, as a function of the day and night and the day number in the year, is a very, very important curve to describe shadings and also the varying water content in the atmosphere and things like that. There is a lot of systematic variation here. So this is one of the basic, this is corresponding to the power curve model we have for wind farms, and then we are using this in a dynamical model as well. I think I will stop. Conclusion is that models should be adaptive. I hope we can convince you about that. it's very, very important to take forecast errors into account if you should gain full economical benefits from the forecast. Use more than one single met provider, and in many cases it's very, very important to take into account correlation in forecast errors as well. And generating these scenarios of forecast can be used to answer a lot of questions. For instance, what is the probability of this storage is lasting up for the next 5 hours? And for instance, what is the probability of increase in wind speed of more than 50% of the installed power over the next 2 hours and things like that? These can be answered by having these tools for scenario generation of forecast, which takes into account both the probabilities or uncertainty and the correlation of the errors. At the end, I have listed a long list of our publications related to